Zoom into a snowflake, a fern, or a coastline, and you find something strange. Patterns repeating themselves, smaller and smaller, almost endlessly. Mathematicians call this fractal geometry. But what if the universe itself follows this same principle? Today, we explore the scientific and philosophical question: is our cosmos a fractal, a self-repeating structure from the smallest particles to the largest galactic webs? Imagine looking at the most detailed map of our universe ever created. You see galaxies scattered across space, like glittering cities connected by vast highways of dark matter. These cosmic superhighways stretch for hundreds of millions of light years, forming an intricate web that looks remarkably similar to the neural networks in your brain, or the delicate veins running through a leaf. This similarity is not just poetic coincidence. It might be revealing something profound about the fundamental nature of reality itself. When we peer into the deepest structures of space and time, we discover patterns that echo across every scale of existence, from the quantum foam of subatomic particles to the grandest filaments of the cosmic web. The ancient philosophers spoke of correspondences between the microcosm and macrocosm, the idea that small-scale patterns reflect larger ones. Modern science has given this intuition a mathematical foundation through fractal geometry, the study of shapes and structures that display self-similarity across different scales of observation. But could this principle extend to the entire universe? Could the cosmos itself be one vast fractal pattern, repeating its geometric signature from the tiniest quantum fluctuations to structures so large they challenge our very conception of space and time? As we embark on this journey through the mathematical cosmos, we will discover how cutting-edge astronomy and theoretical physics are revealing startling connections between the smallest and largest structures in existence, suggesting that our universe might be far stranger and more beautiful than we ever imagined. The patterns we are about to explore could fundamentally change how we understand our place in the infinite tapestry of space and time. Welcome to the fractal cosmos, where every scale tells the same story, and infinity looks back at itself through endless mirrors of mathematical beauty. To understand whether our universe might be a fractal, we first need to grasp what fractals actually are. The word fractal comes from the Latin word fractus, meaning broken or fragmented. But fractals are far more than just broken shapes. They represent one of the most profound mathematical discoveries of the 20th century, revealing hidden patterns that exist everywhere around us. Picture yourself standing on a rocky coastline, watching waves crash against jagged cliffs. From a distance, the coastline appears smooth and curved. But as you walk closer, you notice the edge is actually quite rough and irregular. Get closer still, and you see even more detail. Tiny inlets and rocky outcrops that were invisible from far away. Crouch down with a magnifying glass, and you discover the same jagged, irregular pattern repeating at an even smaller scale. This is the essence of fractal geometry. No matter how much you zoom in, you keep finding similar patterns repeating themselves. The coastline displays what mathematicians call self-similarity across different scales. This property makes fractals fundamentally different from the smooth geometric shapes we learn about in school, like circles, triangles, and squares. The mathematical study of fractals began in earnest during the 1970s with the work of Benoit Mandelbrot, a mathematician working at IBM. Mandelbrot was investigating a simple mathematical question about the length of coastlines, but his research led to discoveries that would revolutionize our understanding of natural patterns. Mandelbrot realized that when you try to measure the length of a coastline, something strange happens. The more accurate your measuring stick becomes, the longer the coastline appears to be. Use a ruler that can measure distances of 1 kilometer, and you get one answer. Use a ruler accurate to 1 meter, and the coastline becomes much longer as you account for all the small bays and inlets. Use a ruler accurate to 1 centimeter, and the coastline becomes longer still as you measure around every pebble and grain of sand. This paradox reveals something fundamental about natural shapes. Unlike the perfect geometric forms we study in mathematics textbooks, real-world objects often have a property called scale invariance. They look essentially the same whether you examine them from far away or up close. The jaggedness you see at one scale is echoed at every other scale you can observe. Consider a piece of Romanesco broccoli, one of nature's most striking examples of fractal geometry. Each spiral cone on the broccoli head is made up of smaller spiral cones, which are themselves composed of even smaller spiral cones. The same spiraling pattern repeats itself across at least 4 or 5 different scales, creating a vegetable that looks like it was designed by a mathematician rather than grown in a garden. Lightning bolts provide another spectacular example of fractal patterns in nature. When lightning strikes, it follows a branching path through the air, creating a main channel with smaller branches splitting off in all directions. But look more closely, and you will see that each of those smaller branches has its own even smaller sub-branches, and those sub-branches split into tiny micro-branches. The same forking, tree-like pattern repeats itself from the massive main bolt down to branches so small they are barely visible to the naked eye. Your own lungs demonstrate fractal geometry on a truly impressive scale. The bronchial tree that carries air into your lungs starts with your trachea, which splits into 2 main bronchi, one for each lung. Each bronchus then divides into smaller bronchi, which split into even smaller bronchioles, and so on. This branching pattern continues through approximately 23 generations of divisions, creating a surface area roughly equivalent to a tennis court packed into the space of your chest cavity. The mathematical beauty of fractals becomes even more apparent when we examine computer-generated examples like the famous Mandelbrot set. This infinitely complex shape is created by a surprisingly simple mathematical rule. For each point on the complex number plane, you repeatedly apply a basic mathematical operation and check whether the result stays bounded or grows without limit. Points that stay bounded are colored black and become part of the Mandelbrot set, while points that grow without bound are colored according to how quickly they escape to infinity. The resulting image is breathtaking in its complexity. The boundary of the Mandelbrot set contains infinitely intricate detail. You can zoom into any part of the boundary and discover new patterns, spirals, and miniature copies of the entire set embedded within the larger structure. Computer programs have been created that can zoom into the Mandelbrot set for hours, revealing layer after layer of mathematical beauty that never repeats exactly, but always maintains the same underlying character. Julia sets, named after the French mathematician Gaston Julia, provide another family of fractal shapes with similar properties. Each Julia set is defined by a different mathematical parameter, creating an infinite variety of fractal patterns. Some Julia sets look like cosmic dust clouds, others resemble delicate lace patterns, and still others appear as abstract art that seems to pulse with hidden energy. What makes these mathematical fractals so remarkable is their infinite detail. No matter how far you zoom in, there is always more complexity to discover. This property of infinite detail packed into a finite area challenges our usual intuitions about geometry and space. Traditional geometric shapes have well-defined perimeters and areas that can be calculated exactly. But fractals exist in a strange mathematical realm where boundaries can have infinite length while enclosing finite areas. The dimension of a fractal provides another mind-bending concept. We are accustomed to thinking of dimension as a simple whole number. A line is one-dimensional, a flat surface is two-dimensional, and the space we live in is three-dimensional. But fractals can have fractional dimensions that fall between these familiar whole numbers. A coastline, for example, is more complex than a simple one-dimensional line because of all its twists and turns, but it is not quite as complex as a two-dimensional surface. Mathematicians have developed techniques to measure the fractal dimension of such objects, and coastlines typically have dimensions somewhere between 1 and 2. The more jagged and convoluted the coastline, the closer its dimension gets to 2. This concept of fractional dimension helps us understand why fractal patterns are so common in nature. Many natural processes, from the growth of plants to the formation of river networks, are governed by physical laws that naturally create structures with fractal properties. These processes tend to fill space in an efficient but irregular way, leading to shapes and patterns that exist in the mathematical realm between traditional geometric dimensions. Scale invariance, the defining property of fractals, appears throughout the natural world because many physical processes operate the same way at different scales. The forces that shape a mountain range over millions of years are fundamentally similar to the forces that create tiny ridges in sand dunes over the course of hours. Gravity, erosion, fluid dynamics, and thermal processes often produce similar patterns, whether they are acting on systems the size of galaxies or systems the size of snowflakes. Understanding fractals gives us a new lens through which to view the complexity of the natural world. Rather than seeing irregularity as random chaos, we can recognize the hidden order that underlies many apparently disordered systems. This mathematical framework has found applications in fields ranging from computer graphics to medical imaging to financial modeling, proving that fractal geometry is not just an abstract mathematical curiosity, but a practical tool for understanding complex systems. The mathematics behind fractals reveals even more surprising properties. When you calculate the area inside a fractal boundary, you often get a finite result. But when you try to calculate the length of the boundary itself, you discover it is infinite. This seems impossible at first glance. How can an infinite perimeter surround a finite area? Yet this is exactly what happens with fractals like the famous Koch snowflake. The Koch snowflake begins as a simple equilateral triangle, but then mathematicians apply a specific rule. Divide each side into 3 equal parts and replace the middle segment with 2 sides of a smaller equilateral triangle pointing outward. This creates a 6-pointed star shape. Now repeat this process on every straight edge of the new shape. Keep repeating this process forever, and you create the Koch snowflake, a shape with infinite perimeter but finite area. This mathematical paradox has profound implications for how we think about space and measurement. In the real world, we encounter similar situations all the time without realizing it. The inner surface of your lungs, folded and refolded through fractal branching, creates an enormous area for gas exchange within the limited volume of your chest. The root system of a tree, branching fractally through the soil, maximizes the surface area for nutrient absorption while fitting into a constrained underground space. Nature seems to have discovered fractal geometry long before mathematicians formalized it. Evolution has repeatedly found that fractal structures provide optimal solutions to many biological challenges. The fractal branching of blood vessels ensures that nutrients can reach every cell in your body through the shortest possible path network. The fractal structure of neural networks in your brain allows for maximum connectivity between neurons while minimizing the total length of neural pathways. Plants demonstrate some of the most beautiful examples of fractal growth patterns. Ferns unfurl their fronds in fractal spirals, with each leaflet being a smaller version of the entire frond. Trees branch in fractal patterns that optimize their ability to capture sunlight while maintaining structural stability against wind loads. Even the arrangement of seeds in a sunflower head follows fractal mathematics, with spiral patterns that pack the maximum number of seeds into the available circular space. The connection between fractals and chaos theory reveals another layer of mathematical beauty. Many chaotic systems, despite their apparent randomness, generate fractal patterns when their behavior is plotted in mathematical phase space. The famous Lorentz attractor, discovered when studying weather patterns, creates a butterfly-shaped fractal that shows how deterministic equations can produce unpredictable but beautifully structured results. This connection between chaos and fractals appears throughout nature. Weather systems create fractal cloud patterns, with large storm systems containing smaller eddies and vortices, which themselves contain even smaller turbulent structures. River deltas branch in fractal patterns as water finds the most efficient paths through sediment. Mountain ranges display fractal profiles created by millions of years of erosion and tectonic activity. The discovery of fractals has revolutionized our understanding of roughness and irregularity in the natural world. Before fractal geometry, scientists often treated irregular shapes as annoying complications that interfered with clean mathematical analysis. Mountains were approximated as cones, coastlines as smooth curves, and clouds as spheres or ellipsoids. But fractals revealed that irregularity itself can be mathematically precise and beautiful. Computer graphics have embraced fractal algorithms to create realistic landscapes and natural textures. Video games and movies now use fractal mathematics to generate convincing mountains, clouds, and alien worlds. The same mathematical principles that govern the branching of lightning bolts can be used to create realistic computer-generated trees, rivers, and geological formations. Financial markets have also been found to exhibit fractal properties. Price movements in stocks, currencies, and commodities show self-similar patterns across different timescales. The volatility you see in minute-by-minute price changes resembles the volatility in daily, monthly, and yearly price movements. This discovery has led to new approaches to financial modeling and risk management, though it has also revealed why financial markets are fundamentally unpredictable over long time periods. The medical field has found numerous applications for fractal analysis. The fractal dimension of heart rhythms can indicate cardiovascular health, with healthy hearts showing more complex fractal patterns than diseased ones. Cancer cells often exhibit different fractal properties than healthy cells, leading to new diagnostic techniques. The fractal structure of bone tissue affects its strength and healing properties, influencing how doctors approach orthopedic treatments. Fractals also appear in the digital realm of computer science and information theory. The structure of the internet itself shows fractal properties, with networks of networks creating self-similar patterns at multiple scales. Data compression algorithms use fractal mathematics to identify and exploit repeating patterns in digital information. Even the binary code that computers use to represent information can exhibit fractal characteristics when analyzed mathematically. The philosophical implications of fractals extend far beyond mathematics and science. If nature consistently creates fractal patterns, what does this tell us about the fundamental structure of reality? Some philosophers have suggested that fractals reveal a kind of mathematical consciousness inherent in the universe, as if physical laws naturally tend toward creating beautiful, complex patterns that exhibit infinite depth. The ancient Greek concept of the golden ratio finds new expression in fractal geometry. Many natural fractals incorporate the golden ratio in their proportional relationships, creating a bridge between classical mathematical beauty and modern complexity theory. The spiral patterns in nautilus shells, pinecone arrangements, and galaxy arms often follow golden ratio mathematics embedded within fractal structures. As we prepare to explore whether the universe itself might be a fractal, these fundamental concepts of self-similarity, scale invariance, and fractional dimension will serve as our guide. The patterns we see in coastlines, broccoli, and lightning bolts may be echoed in the larger structures of the cosmos, suggesting that fractal geometry is not just a mathematical abstraction, but a fundamental principle that governs the organization of matter and energy across all scales of existence. The journey from simple geometric shapes to infinite mathematical complexity reflects humanity's evolving understanding of nature itself. What once seemed chaotic and random now reveals deep mathematical order. What appeared smooth and simple from a distance shows intricate detail upon closer inspection. and what seemed impossible in pure mathematics turns out to be commonplace in the natural world around us. When we look up at the night sky with our naked eyes, the universe appears to be filled with randomly scattered points of light. Stars seem to be sprinkled across the heavens without any obvious pattern or organization. But this impression changes dramatically when we use powerful telescopes to peer deeper into space and map the locations of millions of galaxies across vast cosmic distances. What astronomers have discovered over the past several decades is nothing short of revolutionary. The universe is not randomly organized at all. Instead, galaxies are arranged in an intricate network of filaments, sheets, and nodes that resembles a vast three-dimensional spider web stretching across billions of light years. This cosmic web, as astronomers call it, displays patterns that bear a striking resemblance to the fractal structures we find throughout nature. The story of discovering the cosmic web begins in the early 1970s, when astronomers first started using computers to map the positions of thousands of galaxies in three-dimensional space. The Harvard-Smithsonian Center for Astrophysics conducted one of the first major galaxy surveys, measuring the distances to galaxies by analyzing how their light was shifted toward the red end of the spectrum as the universe expanded. What they found challenged every expectation about cosmic structure. Instead of galaxies being uniformly distributed through space, as many cosmological models predicted, the survey revealed enormous empty regions called voids, surrounded by dense walls and filaments of galaxies. The largest of these structures stretched for hundreds of millions of light years, making them among the biggest known objects in the universe. The most famous early discovery was the Great Wall, a sheet-like structure of galaxies stretching more than 500 million light-years across the sky. This cosmic wall is so large that light takes over 500 million years to travel from one end to the other. Yet despite its enormous size, the Great Wall is relatively thin, only about 15 million light-years thick. This creates a structure with proportions similar to a soap bubble wall, but on a scale that dwarfs anything in human experience. As galaxy surveys became more extensive and precise, the cosmic web revealed ever more intricate details. The Sloan Digital Sky Survey, which began observations in the year 2000, mapped the positions of millions of galaxies across a significant fraction of the observable universe. The resulting three-dimensional maps showed that the cosmic web extends as far as telescopes can see, with no signs of ending or becoming less organized at greater distances. The fractal nature of this cosmic web becomes apparent when you examine it at different scales. At the smallest scales we can observe, individual galaxies cluster together in groups containing anywhere from a few dozen to a few hundred members. Our own Milky Way galaxy belongs to a small group called the Local Group, which contains about 80 galaxies dominated by the Milky Way, the Andromeda Galaxy, and several smaller companions. These galaxy groups are themselves organized into larger structures called galaxy clusters, which can contain thousands of individual galaxies bound together by gravity. The nearest large galaxy cluster to us is the Virgo cluster, located about 54 million light-years away and containing over 1,300 galaxies. The Virgo cluster is so massive that its gravitational pull affects the motion of our local group, slowly drawing us toward its center at a speed of about 400 kilometers per hour. But even galaxy clusters are just intermediate structures in the cosmic hierarchy. Clusters group together into superclusters, vast aggregations containing dozens of galaxy clusters spread across regions hundreds of millions of light-years in diameter. Our local group and the Virgo cluster are both part of the Laniakea supercluster, a structure so large that it contains over 100,000 galaxies and has a total mass of about 10 to the power of 17 times the mass of our Sun. Yet superclusters themselves are not the end of cosmic organization. They are connected by filaments of dark matter and galaxies that stretch across even larger distances. creating a web-like pattern that extends throughout the observable universe. These cosmic filaments can be hundreds of millions of light-years long, but only a few tens of millions of light-years wide, creating structures with extreme length-to-width ratios that resemble cosmic noodles or strings. The spaces between these filaments and sheets of galaxies are not empty. They are filled with cosmic voids, vast regions that contain very few galaxies and appear almost completely empty when compared to the dense filamentary structures surrounding them. The largest known void, called the Bhuta's Void, or Great Nothing, spans approximately 330 million light-years in diameter and contains very few galaxies in its interior. This arrangement of matter creates a cosmic foam-like structure with dense filaments and sheets surrounding vast empty bubbles. The similarity to soap foam is not merely superficial. Both cosmic structure and soap foam are organized by similar mathematical principles related to minimizing surface tension and energy while maximizing volume efficiency. The fractal nature of the cosmic web becomes even more apparent when astronomers measure something called the correlation function, which describes how the clustering of galaxies changes as you look at different distance scales. If galaxies were randomly distributed, this correlation function would show no particular pattern. But observations consistently show that galaxy clustering follows a power law relationship across multiple scales, which is a hallmark of fractal geometry. This power law means that the probability of finding a galaxy at any given distance from another galaxy decreases in a mathematically precise way that remains consistent whether you are looking at separations of millions of light years or hundreds of millions of light years. This scale invariant clustering is exactly what you would expect to see if the universe has fractal properties. The Millennium Simulation, one of the largest computer simulations of cosmic structure formation ever conducted, provides remarkable confirmation that gravity naturally creates fractal-like patterns. This simulation followed the evolution of more than 10 billion particles, representing dark matter, as they clump together under their mutual gravitational attraction over billions of years of cosmic history. The results show that gravitational clustering naturally produces a cosmic web with fractal characteristics. The simulation begins with tiny, nearly random fluctuations in the density of matter shortly after the Big Bang. But as time progresses, gravity amplifies these fluctuations, causing matter to flow from low-density regions into high-density regions. This process creates exactly the kind of hierarchical, self-similar structure that we observe in the real universe. Dark matter, which makes up about 85% of all matter in the universe, plays a crucial role in creating the cosmic web. Because dark matter interacts only through gravity, it can collapse into dense structures without being disrupted by radiation pressure or other electromagnetic forces that affect ordinary matter. This allows dark matter to form the scaffolding of cosmic structure, creating a framework upon which ordinary matter can later condense to form stars and galaxies. The cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space, provides additional evidence for the fractal nature of cosmic structure. Tiny temperature fluctuations in this ancient light, detected by satellites like the Wilkinson Microwave Anisotropy Probe and the Planck Space Telescope, show the seeds of structure that would later grow into the cosmic web we see today. These primordial fluctuations display statistical properties consistent with fractal scaling laws. The same mathematical relationships that describe the clustering of galaxies today can be traced back to quantum fluctuations that occurred during cosmic inflation, the brief period of exponential expansion that occurred in the first fraction of a second after the Big Bang. The discovery that cosmic inflation naturally produces fractal-like fluctuations suggests that fractal geometry may be built into the very foundations of our universe. Quantum mechanics, operating at the smallest possible scales during the inflationary epoch, appears to have imprinted fractal patterns that continue to influence the structure of the universe 13.8 billion years later. Modern galaxy surveys are revealing even more detailed fractal properties of cosmic structure. The Dark Energy Survey, which mapped hundreds of millions of galaxies across a quarter of the southern sky, shows that fractal clustering extends to redshifts corresponding to distances of billions of light years. The upcoming Euclid space mission and the Vera C. Rubin Observatory will map cosmic structure with unprecedented precision, potentially revealing fractal patterns on even larger scales. These observations are beginning to answer fundamental questions about the nature of space and time. If the universe displays fractal properties on all observable scales, it suggests that space itself may have a more complex structure than the smooth, continuous geometry described by Einstein's theory of general relativity. Some theoretical physicists are exploring models in which space-time itself has fractal properties at the smallest quantum scales. The cosmic web also raises profound questions about the ultimate size and extent of the universe. If fractal patterns continue beyond the limits of our current observations, the universe may be vastly larger and more complex than we can currently imagine. The structures we can observe may be just a small sample of patterns that repeat on arbitrarily large scales throughout an infinite cosmic expanse. As we continue to map the cosmic web with ever greater precision, we are not just creating bigger and better catalogues of galaxy positions. We are probing the fundamental mathematical principles that govern the organization of matter and energy across the largest scales in nature. The fractal patterns emerging from these observations suggest that the universe may be far more strange and beautiful than our ancestors ever dared to imagine. The discovery that the universe displays fractal properties raises a fundamental question that has sparked intense debate among cosmologists. Do these fractal patterns continue indefinitely to arbitrarily large scales, or do they eventually fade away, giving way to a smooth and uniform distribution of matter? This question strikes at the heart of our understanding of cosmic structure and challenges some of the most basic assumptions in modern cosmology. The standard model of cosmology, known as lambda cold dark matter or lambda CDM, makes a clear prediction about this issue. According to this model, the universe should become increasingly smooth and uniform when viewed on sufficiently large scales. This prediction, called the cosmological principle, assumes that the universe is both homogeneous, meaning it looks the same everywhere, and isotropic, meaning it looks the same in all directions when averaged over large enough regions. This assumption of large-scale uniformity is not just a mathematical convenience. It forms the foundation for Einstein's equations of general relativity as applied to the entire universe. Without this assumption, the mathematics of cosmology becomes virtually impossible to solve, and we lose our ability to make predictions about the expansion history and ultimate fate of the universe. But observations of the cosmic web seem to challenge this fundamental assumption. Galaxy surveys consistently reveal structure on scales of hundreds of millions of light years, approaching the size of the observable universe itself. Some astronomers argue that we have not yet reached the scale at which the universe becomes truly uniform, raising troubling questions about whether the cosmological principle is actually valid. The debate centers around what is called the transition to homogeneity, the distance scale at which fractal clustering should give way to uniform distribution. Theoretical calculations based on the lambda CDM model suggest this transition should occur at scales of approximately 100 to 300 million light years. Below this scale, galaxies should show strong clustering and fractal-like correlations. Above this scale, the distribution of matter should become smooth and featureless when averaged over large volumes. Early galaxy surveys seem to support this prediction. The first three-dimensional maps of galaxy positions showed strong clustering on small scales, but appeared to become more uniform on the larger scales that could be observed. However, as surveys became larger and more sensitive, astronomers kept discovering structures that exceeded the predicted scale of homogeneity. The discovery of the Great Wall in the 1980s was the first major challenge to the predicted transition scale. This structure stretches for more than 500 million light-years, well beyond the scale at which the universe was supposed to become homogeneous. Subsequent surveys have revealed even larger structures, including superclusters and filaments that span significant fractions of the observable universe. One of the most controversial discoveries came from the analysis of gamma-ray bursts, the most energetic explosions known in the universe. These cosmic beacons are so bright that they can be seen across billions of light-years, allowing astronomers to map cosmic structure on truly enormous scales. Some studies of gamma-ray burst distributions have claimed to find clustering patterns extending to scales of several billion light-years, far larger than any structures predicted by standard cosmological models. The Huge Large Quasar group, discovered in 2013, provides another example of unexpectedly large-scale structure. This collection of 73 quasars spans approximately 4 billion light-years, making it one of the largest known structures in the universe. According to the cosmological principle, structures this large should not exist, yet observations clearly show that they do. These discoveries have led some astronomers to question whether the transition to homogeneity occurs at all within the observable universe. Luciano Pietronero, an Italian physicist, has been one of the most vocal advocates for the idea that the universe displays fractal properties on all observable scales. His analysis of galaxy survey data suggests that fractal clustering continues without any clear transition to uniformity, even on scales approaching the size of the observable universe. Pietronero's fractal cosmology model proposes that the universe is fundamentally inhomogeneous, with fractal clustering patterns extending indefinitely. In this view, the assumption of large-scale homogeneity is not just incorrect, but fundamentally misleading. The universe would be more like an infinite fractal structure, with no characteristic scale at which it becomes smooth and uniform. This radical proposal has significant implications for our understanding of cosmic evolution and the Big Bang itself. If the universe is fundamentally fractal, then the standard interpretation of the cosmic microwave background radiation and the expansion history of the universe may need to be completely reconsidered. The redshift distance relationship that forms the basis for measuring cosmic expansion could be affected by large-scale inhomogeneities in ways that current models do not account for. However, most cosmologists remain skeptical of such extreme claims. They point to several lines of evidence that support the eventual transition to homogeneity. The cosmic microwave background radiation, which provides a snapshot of the universe when it was only 380,000 years old, shows temperature variations of only a few parts in 100,000. This high degree of uniformity suggests that the universe was extremely smooth in its early stages, before gravity had time to amplify small density fluctuations into large-scale structure. Statistical analyses of galaxy survey data also support the existence of a transition scale, though there is ongoing debate about exactly where this transition occurs. Most studies find that galaxy correlations become progressively weaker on larger scales and approach zero on scales of several hundred million light-years. This behavior is consistent with the predicted transition to homogeneity, though the transition may occur at somewhat larger scales than originally expected. The challenge in resolving this debate lies partly in the difficulty of measuring homogeneity accurately. Galaxy surveys are limited by selection effects, observational biases, and finite sample sizes that can create apparent clustering, even in truly random distributions. Distinguishing between real large-scale structure and statistical noise requires extremely careful analysis and large data sets. The finite size of the observable universe also complicates the analysis. Even if the universe becomes homogeneous on scales of several 100 million light-years, we can only observe a sphere with a radius of about 46 billion light-years. This means we can only sample a limited number of independent regions at the largest scales, making it difficult to determine conclusively whether the universe is truly homogeneous. Recent advances in observational cosmology are beginning to provide more definitive answers to these questions. The Planck satellite's measurements of the cosmic microwave background show that the universe is remarkably uniform on large scales when viewed in the microwave portion of the electromagnetic spectrum. Temperature fluctuations in this ancient light correspond to density variations that are extremely small, supporting the idea that the universe becomes increasingly smooth on larger scales. Large-scale galaxy surveys are also providing new insights into the transition to homogeneity. The Baryon Oscillation Spectroscopic Survey, part of the Sloan Digital Sky Survey, has mapped the positions of over 1 million galaxies across enormous volumes of space. These observations show clear evidence for the predicted transition scale, with galaxy clustering becoming progressively weaker on scales larger than about 150 million light-years. The Dark Energy Survey has extended these measurements to even larger scales and greater distances. By mapping hundreds of millions of galaxies across a quarter of the sky, this survey has been able to measure cosmic homogeneity with unprecedented precision. The results support the existence of a transition to homogeneity on scales of approximately 300 million light-years, consistent with the predictions of the Lambda CDM model. Computer simulations provide another powerful tool for understanding the transition to homogeneity. The Millennium simulation and its successors can follow the gravitational evolution of cosmic structure from shortly after the Big Bang to the present day. These simulations consistently predict that fractal clustering should give way to large-scale uniformity on scales of a few 100 million light-years. The simulations also help explain why some observations appear to show structure on larger scales than expected. Random fluctuations in any finite sample will occasionally produce apparent structures that are larger than the typical clustering scale. These statistical fluctuations can create the illusion of large-scale structure even in a universe that is fundamentally homogeneous above a certain scale. The debate over cosmic homogeneity has important implications for our understanding of dark energy, the mysterious force that appears to be accelerating the expansion of the universe. Measurements of cosmic acceleration rely on the assumption that the universe is homogeneous on large scales. If this assumption is incorrect, then apparent evidence for dark energy could actually be the result of our location in an unusually empty region of space. Some alternative cosmological models propose that we live in a giant cosmic void, a region where the density of matter is significantly lower than the cosmic average. From our perspective, inside such a void, distant galaxies would appear to be receding faster than expected, creating the illusion of cosmic acceleration. This scenario could potentially explain the apparent effects of dark energy without requiring any new physics. However, most observational evidence argues against such large-scale inhomogeneity. The cosmic microwave background shows no evidence for the large-scale temperature variations that would be expected if we lived in a significant void. Measurements of distant supernovae and other cosmic distance indicators also support the idea that cosmic acceleration is a real phenomenon rather than an artifact of large-scale structure. The question of whether fractal patterns have a maximum scale remains one of the most fundamental unsolved problems in cosmology. The answer will ultimately depend on more extensive observations and improved theoretical understanding of how gravity shapes cosmic structure. Future galaxy surveys, including those planned for the next generation of ground-based and space-based telescopes, will map cosmic structure with unprecedented precision and may finally resolve the debate over the transition to homogeneity. The implications of this research extend far beyond academic cosmology. If the universe truly displays fractal properties on all observable scales, it would represent a fundamental paradigm shift in our understanding of space, time, and matter. It would suggest that the mathematical principles governing small-scale natural phenomena also operate on the largest scales in the universe, creating a deep connection between the microscopic and macroscopic worlds that we are only beginning to understand. While the cosmic web provides the most dramatic example of fractal patterns in the universe, these mathematical structures appear throughout physics at every scale we can observe. From the quantum realm of subatomic particles to the classical world of everyday objects, fractal geometry seems to be a fundamental organizing principle that governs how matter and energy arrange themselves in space and time. In the world of high-energy particle physics, some of the most spectacular examples of fractal patterns emerge from the collision experiments conducted at facilities like the Large Hadron Collider at CERN. When protons smash into each other at energies approaching the speed of light, they create showers of secondary particles that spray outward in complex branching patterns. These particle jets display remarkably clear fractal characteristics, with large angle deflections spawning smaller deflections, which in turn create even smaller branching angles. The mathematics describing these particle jets follows the same power law relationships that characterize other fractal phenomena in nature. The probability of finding a particle at any given angle from the main jet direction decreases according to a precise mathematical formula that remains valid across multiple scales of observation. This scale invariant behavior suggests that the fundamental forces governing particle interactions operate in ways that naturally create fractal structures. Quantum chromodynamics, the theory that describes the strong nuclear force binding quarks together inside protons and neutrons, provides a theoretical framework for understanding these fractal patterns. The equations of quantum chromodynamics predict that high-energy collisions should produce cascading showers of particles with self-similar branching structures. The agreement between these theoretical predictions and experimental observations provides strong evidence that fractal geometry is built into the fundamental laws of physics. Even more remarkably, the fractal dimension of particle jets carries information about the underlying physics of the collision. Different types of particles and different collision energies produce jets with slightly different fractal properties. Physicists have learned to use these fractal characteristics as diagnostic tools for identifying new particles and testing theoretical predictions about the behavior of matter under extreme conditions. The quantum world reveals fractal structures in other surprising contexts as well. When electrons are confined to two-dimensional surfaces and subjected to strong magnetic fields, they can form exotic states of matter called quantum Hall liquids. The wave functions describing these quantum states often have fractal boundaries that separate regions where electrons are likely to be found from regions where they are unlikely to exist. These quantum fractal wave functions are not just mathematical curiosities. They correspond to real physical phenomena that can be measured in laboratory experiments. The fractal dimension of the wave function boundary affects the electrical conductivity of the material, creating measurable signatures that physicists can detect with sensitive electronic instruments. Quantum chaos theory provides another arena where fractal patterns emerge from the fundamental laws of physics. When quantum mechanical systems exhibit chaotic behavior, their energy levels and wave functions often display fractal characteristics. The famous quantum billiards experiments, where particles bounce around inside irregularly shaped enclosures, create wave patterns with fractal boundaries that reflect the underlying chaotic dynamics. These quantum fractal phenomena suggest that the boundary between order and chaos is itself fractal in nature. Systems that are too simple become boring and predictable, while systems that are too complex become completely random and unpredictable. But at the fractal boundary between these extremes, systems exhibit the kind of complex, structured behavior that we observe throughout the natural world. Percolation theory, a branch of mathematics that studies how connectivity emerges in random networks, reveals another deep connection between fractals and fundamental physics. When you randomly place conducting links on a lattice and gradually increase their density, there comes a critical point where a connected path suddenly appears spanning the entire system. This percolation transition creates fractal clusters of connected and disconnected regions that display scale-invariant properties. Percolation transitions occur throughout physics in contexts ranging from the flow of oil through porous rock to the spread of forest fires across landscapes. The fractal geometry of percolation clusters determines many important physical properties, including electrical conductivity, mechanical strength, and fluid flow rates. Understanding these fractal relationships has practical applications in fields ranging from petroleum engineering to epidemiology. Phase transitions in general often involve fractal phenomena. When water freezes into ice, the boundary between the liquid and solid phases can develop fractal characteristics under certain conditions. The dendritic patterns of frost on a window pane or the complex shapes of snowflakes both emerge from fractal growth processes that operate at the molecular level. Critical phenomena, which occur at phase transition points, are particularly rich sources of fractal behavior. Near a critical temperature, materials develop correlations that extend over arbitrarily large distances, creating fractal patterns in their microscopic structure. The correlation length, which measures how far these patterns extend, diverges as a power law near the critical point, another signature of fractal scaling. The study of turbulence has revealed some of the most complex and beautiful fractal patterns in classical physics. When fluids flow at high speeds, they develop chaotic motion characterized by eddies within eddies within eddies, creating a cascade of motion across multiple length scales. This turbulent cascade follows fractal scaling laws that relate the size of eddies to their rotational energy and dissipation rates. The famous energy cascade of turbulence, first described by Andrei Kolmogorov in 1941, shows how kinetic energy flows from large-scale motions down to progressively smaller scales until it is finally dissipated as heat at the molecular level. This cascade process creates fractal velocity fields with well-defined scaling relationships that have been confirmed in countless experiments and numerical simulations. Atmospheric turbulence provides particularly striking examples of fractal fluid dynamics. Cloud formations often display fractal boundaries that reflect the turbulent mixing of air masses with different temperatures and humidity levels. The fractal dimension of cloud edges affects how much solar radiation they absorb and reflect, influencing weather patterns and climate dynamics. Ocean currents also exhibit fractal properties that affect global climate patterns. The Gulf Stream and other major currents develop meandering patterns with fractal characteristics that influence how heat is transported between different regions of the Earth. Understanding these fractal ocean dynamics is crucial for predicting long-term climate change and improving weather forecasting models. Plasma physics, the study of ionized gases that make up stars and much of the visible matter in the universe, reveals fractal phenomena on truly cosmic scales. Solar flares and coronal mass ejections from our Sun create fractal patterns of magnetic field lines and charged particle flows that can affect satellite communications and power grids on Earth. The magnetic field structure of the Sun itself displays fractal characteristics that emerge from the complex interplay between plasma motion and magnetic forces. Solar physicists have discovered that the distribution of magnetic field strengths follows power law scaling relationships characteristic of fractal systems. These fractal magnetic patterns may help explain the 11-year solar cycle and other periodic variations in solar activity. Lightning provides one of the most visually spectacular examples of fractal patterns in atmospheric physics. The stepped leader that precedes a lightning strike follows a fractal path through the air as it searches for the most efficient route to the ground. The branching pattern of lightning channels displays clear self-similarity across multiple scales, from the main discharge channel down to tiny branch structures visible only in high-speed photography. The physics of lightning formation involves fractal phenomena at multiple levels. The initial breakdown of air molecules creates fractal networks of ionized channels that compete with each other to form the final discharge path. The fractal dimension of the lightning channel affects its electrical resistance and the amount of current it can carry, influencing the brightness and duration of the flash. Fractal geometry also appears in the study of crystal growth and material science. When crystals grow under conditions far from equilibrium, they often develop fractal surfaces and internal structures. Diffusion-limited aggregation, a process where particles stick together as they randomly walk through space, creates fractal clusters with universal scaling properties that appear in contexts ranging from bacterial colonies to mineral formations. The fractal nature of crystal defects affects the mechanical properties of materials in ways that engineers are just beginning to understand. Crack propagation in metals and ceramics often follows fractal paths that determine the strength and failure characteristics of structural components. Understanding these fractal failure patterns is crucial for designing safer buildings, bridges, and aircraft. Semiconductor physics has revealed fractal phenomena in the electronic properties of advanced materials. Quantum dots and other nanostructures can exhibit fractal energy spectra that affect their optical and electrical properties. These fractal electronic states are being explored for applications in quantum computing and advanced solar cell technologies. The emergence of fractal patterns across so many different areas of physics suggests that these mathematical structures reflect something fundamental about how the laws of nature operate. Whether we are studying the collision of elementary particles or the formation of galaxies, the growth of crystals or the turbulent flow of fluids, we consistently find that nature organizes itself according to fractal principles. This universality of fractal behavior points toward deep connections between apparently unrelated physical phenomena. The same mathematical relationships that describe the branching of lightning bolts also apply to the clustering of galaxies, the formation of river networks, and the structure of quantum wave functions. This suggests that fractal geometry may be more than just a mathematical tool for describing complex shapes. It may represent a fundamental organizing principle that governs how matter and energy arrange themselves across all scales of the physical universe. As our understanding of fractal physics continues to develop, we are beginning to see how these mathematical structures might provide a unified framework for understanding complexity in nature. The fractal patterns that appear throughout physics may be telling us something profound about the underlying structure of reality itself, revealing connections between the quantum and classical worlds that we are only beginning to explore. Gravity, the weakest of the four fundamental forces, paradoxically creates some of the most spectacular and largest fractal structures in the universe. Unlike electromagnetic forces that can both attract and repel, gravity only attracts, always pulling matter together into increasingly dense concentrations. This simple fact has profound consequences for how structure forms and evolves throughout cosmic history, leading to the hierarchical, self-similar patterns we observe across all astronomical scales. The story of gravitational clustering begins in the earliest moments after the Big Bang, when the universe was filled with an almost perfectly smooth distribution of matter and energy. But this primordial smoothness contained tiny irregularities, quantum fluctuations that were stretched to cosmic scales during the brief period of exponential expansion known as cosmic inflation. These minute density variations, amounting to differences of only a few parts in 100,000, would eventually grow under the influence of gravity to become the galaxies, stars, and cosmic structures we see today. The mathematics of gravitational instability, first worked out by James Jeans in the early 1900s, explains how these small perturbations grow over time. In regions where the density is slightly higher than average, the gravitational pull is stronger, causing matter to flow inward from surrounding areas. This makes the high-density regions even denser, which strengthens their gravitational pull even more, creating a runaway process that amplifies tiny initial fluctuations into large-scale structure. This gravitational amplification process naturally creates fractal patterns because it operates the same way at all scales simultaneously. Small density fluctuations grow into small clumps of matter, while larger fluctuations take longer to collapse, but eventually form bigger structures. The result is a hierarchy of structures, with smaller objects embedded within larger ones, creating the nested, self-similar patterns characteristic of fractal geometry. Computer simulations of cosmic structure formation provide stunning visual confirmation of this process. The most sophisticated of these simulations, such as the Millennium Run and the Illustris project, follow the gravitational evolution of billions of particles representing dark matter and ordinary matter from shortly after the Big Bang to the present day. The results show the universe evolving from nearly uniform initial conditions into an intricate cosmic web of filaments, walls, and voids that closely matches what we observe through telescopes. These simulations reveal that gravitational clustering naturally produces structures with fractal characteristics across an enormous range of scales. Dark matter halos, the gravitationally bound structures that host galaxies and galaxy clusters, display fractal substructure with smaller halos embedded within larger ones in a pattern that repeats across multiple levels of the hierarchy. This hierarchical structure emerges spontaneously from the mathematics of gravitational collapse, without any special initial conditions or fine-tuning. The fractal nature of gravitational clustering can be understood through the lens of scale-free collapse. When a region of space has a density that exceeds the cosmic average by a certain critical threshold, it will eventually separate from the general expansion of the universe and collapse to form a gravitationally bound object. The remarkable feature of this process is that it operates identically at all mass scales, from objects with the mass of small asteroids to structures containing the mass of billions of galaxies. This scale-free nature of gravitational collapse means that the same physical processes that create planetary systems also create galaxy clusters, just on vastly different scales of space and time. The mathematical relationships governing the collapse remain unchanged, whether we are dealing with the formation of a solar system over millions of years, or the assembly of a galaxy cluster over billions of years. N-body simulations, which track the gravitational interactions between large numbers of particles, demonstrate this scale invariance in remarkable detail. When researchers analyze the mass distribution in these simulations, they consistently find power law relationships between different scales that are characteristic of fractal systems. The probability of finding a clump of matter with a given mass decreases as a power of that mass, following mathematical relationships that remain valid across many orders of magnitude. The Press-Schechter formalism, developed in the 1970s, provides a theoretical framework for understanding this hierarchical mass distribution. This mathematical approach predicts how many objects of each mass should exist at any given time in cosmic history, based on the statistics of density fluctuations and the dynamics of gravitational collapse. The predictions match observations remarkably well, confirming that gravitational clustering follows universal scaling laws. Galaxy formation within dark matter halos provides a particularly clear example of fractal structure formation. Dark matter, which interacts only through gravity, collapses first to form the scaffolding of cosmic structure. Ordinary matter then falls into these dark matter halos, where it can cool, condense, and eventually form stars and galaxies. This process naturally creates a fractal hierarchy, with smaller galaxies orbiting within larger systems in patterns that repeat across multiple scales. Our own Milky Way galaxy demonstrates this hierarchical structure clearly. The Milky Way is surrounded by dozens of smaller satellite galaxies, including the large and small Magellanic Clouds, which are themselves surrounded by even smaller dwarf galaxies and globular clusters. Observations with the Gaia Space Telescope have revealed that many of these satellite systems show evidence of their own substructure, with streams of stars and smaller stellar associations creating fractal patterns within the larger galactic neighborhood. The local group, containing the Milky Way, Andromeda, and their satellite galaxies, is itself part of a larger fractal hierarchy. This small galaxy group belongs to the Virgo supercluster, which contains dozens of galaxy groups and clusters arranged in a complex web-like pattern. The Virgo supercluster is in turn part of an even larger structure called Laniakea, demonstrating that gravitational clustering creates fractal patterns that extend across hundreds of millions of light-years. Observations of galaxy clustering at different cosmic epochs reveal how these fractal patterns evolve over time. Deep field observations with the Hubble Space Telescope and other advanced instruments show that galaxies in the early universe were more uniformly distributed than they are today. As cosmic time progressed, gravitational clustering amplified the initial density fluctuations, creating increasingly pronounced fractal structure. This evolution of fractal clustering follows predictable mathematical patterns that can be calculated from the theory of gravitational instability. In the early universe, when density fluctuations were small, the clustering was weak and showed only mild departures from uniformity. But as these fluctuations grew under gravity, the clustering became stronger and more fractal-like, eventually producing the highly structured cosmic web we observe today. The role of dark energy in this process adds another layer of complexity to gravitational clustering. Dark energy, which appears to be accelerating the expansion of the universe, opposes the gravitational clustering of matter on large scales. This creates a competition between the attractive force of gravity and the repulsive effect of dark energy, with gravity winning on small scales where matter is dense enough to overcome cosmic expansion. This competition between gravity and dark energy helps explain why fractal clustering appears to have a maximum scale. Below a certain threshold, roughly a few hundred million light-years, gravity dominates and can pull matter together into bound structures. Above this scale, dark energy dominates and prevents further gravitational collapse, leading to the transition to homogeneity that we discussed in earlier chapters. Computer simulations that include dark energy effects show exactly this behavior. The fractal patterns of gravitational clustering grow and evolve on small and intermediate scales, but they are suppressed on the larger scales where dark energy becomes important. This provides a natural explanation for why the universe appears fractal on some scales, but homogeneous on others. The cosmic microwave background radiation preserves a record of the density fluctuations that seeded all subsequent structure formation. The tiny temperature variations in this ancient light correspond to the density fluctuations that would later grow into the cosmic web. Remarkably, these primordial fluctuations already show statistical properties characteristic of fractal systems, suggesting that fractal geometry was imprinted on the universe during its earliest moments. Analysis of the cosmic microwave background reveals that the initial density fluctuations followed a nearly scale-invariant power spectrum, meaning that fluctuations of different sizes had similar amplitudes when properly normalized. This scale invariance in the initial conditions naturally leads to fractal clustering as these fluctuations evolve under gravity, providing a direct link between quantum processes in the early universe and the large-scale structure we observe today. The inflationary model of cosmic expansion provides a theoretical explanation for why the initial fluctuations had this fractal-like character. During inflation, quantum fluctuations in the inflaton field that drove the exponential expansion were stretched to cosmic scales and frozen in as density perturbations. The quantum origin of these fluctuations naturally produces the scale invariant spectrum that leads to fractal clustering. Recent observations of gravitational lensing, where the gravity of massive structures bends and distorts light from more distant sources, provide new ways to study fractal clustering. The distortions in galaxy shapes caused by gravitational lensing reveal the distribution of dark matter on scales, ranging from individual galaxy halos to massive galaxy clusters. These observations confirm that dark matter clustering follows the same fractal patterns predicted by gravitational instability theory. Weak lensing surveys, which measure tiny distortions in the shapes of millions of distant galaxies, are beginning to map the fractal structure of dark matter with unprecedented precision. These surveys reveal that the cosmic web extends far beyond what we can see with ordinary telescopes, confirming that gravitational clustering creates fractal patterns throughout the dark matter that dominates cosmic structure. The study of gravitational clustering has also revealed connections between cosmic structure formation and other fractal phenomena in nature. The same mathematical techniques used to analyze galaxy clustering have been applied to study the distribution of earthquakes, the branching patterns of river networks, and the structure of biological systems. This universality suggests that gravitational clustering may be just one example of a more general class of growth processes that naturally create fractal structures. As our observational capabilities continue to improve, we are gaining ever more detailed views of how gravitational clustering creates fractal patterns across cosmic history. Future surveys with next-generation telescopes will map cosmic structure with extraordinary precision, potentially revealing fractal properties that extend to even larger scales and earlier cosmic epochs. These observations will test our understanding of how gravity shapes the universe and may reveal new connections between the quantum realm and the cosmic web. The possibility that our universe might be infinite opens up some of the most mind-bending concepts in all of cosmology. If space extends forever in all directions, and if the fractal patterns we observe locally continue throughout this infinite expanse, then we are confronted with a cosmos that contains not just vast numbers of galaxies and stars, but infinite repetitions of every possible arrangement of matter and energy that the laws of physics allow. The question of cosmic infinity has puzzled philosophers and scientists for millennia. Ancient Greek thinkers like Democritus proposed that space might be infinite and filled with countless worlds, while others argued that infinity was a mathematical abstraction that could not exist in physical reality. Modern cosmology has brought sophisticated mathematical tools to bear on this ancient question, but the answers we have found are no less strange than the speculations of the ancient philosophers. Einstein's theory of general relativity allows for universes with a variety of different geometries, some finite and some infinite. In a flat universe, which observations suggest describes our cosmos quite accurately, space extends infinitely in all directions. There are no edges or boundaries where space comes to an end. If you could somehow travel far enough in any direction, you would never reach a wall or barrier that marks the limit of the universe. You would simply encounter more space, more galaxies, and more cosmic structure extending forever. But infinity in space raises profound questions about the nature of cosmic structure and the patterns we observe around us. If the universe is truly infinite, and if matter is distributed in a statistically uniform way throughout this infinite space, then every possible arrangement of atoms, stars, and galaxies must occur somewhere. Not only must they occur, but they must occur infinitely many times, scattered throughout the endless cosmic expanse. This leads to what cosmologists call the infinite universe hypothesis, one of the most remarkable and counterintuitive predictions of modern physics. According to this idea, there are infinitely many regions of space that are identical to our observable universe in every detail. Somewhere out there, separated from us by unimaginably vast distances, there is another Milky Way galaxy with another Earth orbiting another sun that is exactly like ours. On that distant Earth, an exact copy of you is reading these exact same words at this exact same moment. The mathematics behind this startling conclusion comes from information theory and probability, Any finite region of space can only contain a finite amount of information, determined by the number of particles it contains and the number of possible ways those particles can be arranged. Even if this number is astronomically large, it is still finite. In an infinite universe, every possible finite arrangement must occur infinitely many times, simply because there is infinite space available and only a finite number of ways to arrange matter within any given volume. The observable universe, the spherical region centered on Earth from which light has had time to reach us since the Big Bang, contains roughly 10 to the power of 80 particles. The number of possible ways to arrange these particles is unimaginably large, but it is still mathematically finite. In an infinite universe, this exact arrangement must be repeated infinitely many times at different locations throughout space. This repetition occurs not just for the overall arrangement of particles, but for every possible subset and variation as well. There are infinitely many regions where the arrangement is almost identical to ours, but with tiny differences. There are versions where Earth formed with slightly different continents, where the dinosaurs never went extinct, where human history unfolded in completely different ways. Every story that could possibly be written, every symphony that could ever be composed, every conversation that could ever take place, all exist somewhere in the infinite multiverse of possibilities. The concept of infinite repetition extends beyond just rearrangements of existing matter. If cosmic inflation, the period of exponential expansion in the early universe, continued for an infinite time in some regions, then it would have created infinite volumes of space with different physical properties. Some regions might have different values for the fundamental constants of physics. Others might have different numbers of spatial dimensions or entirely different laws governing the behavior of matter and energy. This eternal inflation scenario, proposed by cosmologists like Alan Guth and André Linde, suggests that our observable universe is just one bubble in an infinite foam of expanding space-time regions. Each bubble universe could have its own unique properties, its own version of physics, and its own patterns of cosmic structure. The fractal patterns we observe in our cosmic neighborhood might be just one example of infinitely many different types of structure that exist throughout the greater multiverse. The implications of infinite fractal patterns in an infinite universe challenge our most basic concepts of uniqueness and identity. If there are infinitely many copies of every possible arrangement of matter, then concepts like rarity, uniqueness, and even individual identity become problematic. Are you unique if there are infinitely many exact copies of you scattered throughout infinite space? What makes any particular arrangement of atoms special if that same arrangement occurs infinitely many times? These questions touch on deep philosophical issues that go beyond science into the realm of metaphysics and personal identity. Some philosophers argue that infinite repetition does not diminish the value or significance of any particular instance. Others suggest that infinite universes force us to completely rethink what we mean by existence, consciousness, and personal identity. From a more practical scientific perspective, the infinite universe hypothesis makes predictions that might be testable through careful observation. If the universe is infinite and statistically uniform, then the cosmic microwave background radiation should show specific statistical properties that differ from what we would expect in a finite universe. The patterns of temperature fluctuations in this ancient light should exhibit correlations that extend to the largest observable scales. Recent observations with the Planck satellite have searched for evidence of these infinite universe signatures in the cosmic microwave background. The results are intriguing, but not conclusive. Some statistical anomalies in the data might be consistent with infinite space, but they could also be explained by other effects, or simply represent statistical fluctuations in a finite data set. The topology of space provides another avenue for investigating cosmic infinity. Even in an infinite universe, space might be connected in unexpected ways that create the illusion of repetition without requiring actual infinite duplication. Imagine a universe shaped like a three-dimensional torus, where traveling far enough in any direction brings you back to your starting point. Such a universe could be finite in volume, but connected in a way that creates repeating patterns across space. Observations of the cosmic microwave background have searched for evidence of such topological connections by looking for repeated patterns that might indicate we are seeing the same regions of space from different angles. So far, no convincing evidence for such cosmic topology has been found, but the searches continue and may eventually reveal the true shape of space on the largest scales. The fractal nature of cosmic structure adds another layer of complexity to questions about infinite universes. If fractal patterns continue to arbitrarily large scales, then the universe might be infinite, not just in extent, but also in structural complexity. Instead of eventually becoming uniform and featureless, space might contain fractal patterns that never end, with larger and larger structures embedded within one another in an endless hierarchy. This possibility leads to what some cosmologists call the fractal universe model, where space has a fractal dimension greater than 3. In such a universe, the amount of matter within any given radius would grow faster than the volume of space itself, creating a cosmic structure unlike anything predicted by standard cosmological models. The galaxy distributions we observe might be just the smaller scale features of a cosmic fractal that extends to unimaginably large scales. Computer simulations of fractal universe models have explored how such structures might form and evolve over cosmic time. These simulations suggest that fractal cosmic structure could arise naturally from certain types of initial conditions, without requiring any exotic physics or modifications to Einstein's theory of gravity. The key insight is that gravitational clustering can amplify small-scale fractal patterns into large-scale fractal structure under the right circumstances. The observational signatures of a fractal universe would be subtle, but potentially detectable with sufficiently large galaxy surveys. The statistical properties of galaxy clustering would show deviations from the predictions of standard cosmological models that could be measured with careful analysis. Future surveys planned for the next decade may have the sensitivity needed to detect these fractal signatures, if they exist. Quantum mechanics adds yet another dimension to questions about infinite cosmic patterns. In the many worlds interpretation of quantum mechanics, every quantum measurement creates a branching of reality into multiple parallel universes, corresponding to all possible measurement outcomes. If this interpretation is correct, then there are not just infinitely many classical arrangements of matter, but infinitely many quantum versions of reality, branching off from every quantum event. This quantum multiverse would contain every possible variation of cosmic history that is consistent with the laws of quantum mechanics. There would be universes where quantum tunneling caused stars to form in different patterns, where radioactive decay happened at different rates, where the fundamental particles combined in slightly different ways. The fractal patterns we observe in our universe would be just one branch of an infinitely branching tree of quantum possibilities. The anthropic principle provides one framework for thinking about infinite cosmic patterns and their implications for our existence. In an infinite multiverse containing every possible arrangement of matter and energy, most regions would be completely hostile to life as we know it. Only a tiny fraction of infinite space would have the right conditions for stars, planets, and complex chemistry to develop. Yet because infinity is so vast, even this tiny fraction would contain infinitely many life-bearing worlds. From this perspective, the particular fractal patterns we observe in our cosmic neighborhood might be precisely tuned to allow for the emergence of complexity and life. The hierarchical structure of cosmic matter, from stars to galaxy clusters, creates the stable gravitational environments needed for planetary systems and the chemical processes that lead to biology. If cosmic structure were organized differently, Perhaps following different fractal patterns or scaling laws, life might never have had the chance to emerge. As our observational capabilities continue to improve, we may eventually be able to answer some of these profound questions about cosmic infinity and fractal patterns. The next generation of extremely large telescopes will be able to see further into space and further back in cosmic time than ever before, potentially revealing whether fractal structure continues to the largest observable scales. Space-based gravitational wave detectors may provide entirely new ways to probe the structure of space-time itself, testing whether the fabric of reality has fractal properties at the most fundamental level. Whether the universe is finite or infinite, whether fractal patterns continue forever or eventually give way to uniformity, the very fact that we can ask these questions represents one of the most remarkable achievements of human intellect. We have learned to use mathematics and observation to probe the deepest mysteries of existence, revealing a cosmos far stranger and more beautiful than our ancestors could have imagined. The infinite fractal universe, if it exists, would represent the ultimate expression of mathematical beauty made manifest in physical reality. The question of whether the universe displays fractal properties on all scales has sparked one of the most heated debates in modern cosmology. On one side stand astronomers who point to decades of galaxy survey data showing clear evidence for fractal clustering extending to the largest observable scales. On the other side are cosmologists who argue that apparent large-scale structure is either statistical noise or the result of observational biases, and that the universe becomes smooth and homogeneous beyond a certain scale, as predicted by standard cosmological models. This scientific controversy goes beyond mere academic disagreement. The resolution of this debate will determine whether we need to fundamentally revise our understanding of cosmic structure, dark energy, and even the basic assumptions underlying modern cosmology. The stakes could not be higher, as the fractal universe hypothesis challenges some of the most cherished principles that have guided cosmological research for nearly a century. The debate began in earnest during the 1980s, when the first large-scale galaxy surveys started revealing unexpected structure in the cosmic web. The Harvard-Smithsonian Center for Astrophysics Redshift Survey, one of the pioneering efforts to map galaxy positions in 3 dimensions, uncovered the famous Great Wall, a sheet-like structure of galaxies stretching across hundreds of millions of light-years. This discovery was troubling because structures of this size were not expected to exist according to the prevailing cosmological models of the time. As galaxy surveys became larger and more sophisticated, they continued to reveal structures that seemed to exceed the predicted scale of homogeneity. The Las Campanas Redshift Survey, the 2-degree field galaxy Redshift Survey, and eventually the massive Sloan Digital Sky Survey all found evidence for galaxy clustering and large-scale structure extending to the limits of their observational reach. Luciano Pietronero, a physicist at the University of Rome, emerged as one of the most vocal advocates for the fractal universe interpretation of these observations. Working with collaborators like Yuri Barishev and Francesco Silos Labini, Pietronero conducted detailed statistical analyses of galaxy survey data that consistently showed fractal scaling relationships extending to scales of hundreds of millions of light-years, far beyond where standard models predicted the transition to homogeneity should occur. Pietronero's team argued that the galaxy distribution follows a fractal pattern with a dimension of approximately 2, meaning that the number of galaxies within any given radius grows as the square of that radius, rather than as the cube expected for uniform 3-dimensional distribution. This fractal scaling appeared to hold across multiple orders of magnitude in distance, from scales of a few million light-years up to the largest scales probed by the surveys. The implications of Pietronero's analysis were radical. If correct, they would mean that the fundamental assumption of large-scale homogeneity underlying modern cosmology is simply wrong. The universe would be fundamentally inhomogeneous, organized according to fractal principles, rather than the smooth, uniform geometry assumed by Einstein's field equations as applied to cosmology. Critics of the fractal interpretation raised several objections to these claims. One of the most important concerns was the issue of finite sample effects. Galaxy surveys, no matter how large, can only observe a finite number of galaxies within a finite volume of space. In any finite sample, random clustering will occasionally produce apparent structures that appear larger than the true clustering scale. The question is whether the large-scale structures observed in galaxy surveys represent real cosmic organization or merely statistical fluctuations in finite datasets. Michael Turner, a prominent cosmologist at the University of Chicago, was among those who argued that apparent large-scale structure could be explained by these statistical effects. He and his collaborators showed that even in a universe that becomes perfectly uniform on large scales, finite galaxy surveys would occasionally show apparent clustering and structure extending to the limits of the survey volume. The debate was further complicated by issues related to survey selection effects and observational biases. Galaxy surveys are not perfect random samples of cosmic structure. They are limited by the brightness and detectability of galaxies, by dust extinction that obscures distant objects, and by the finite time available for observations. These selection effects can create apparent clustering patterns that do not reflect the true underlying distribution of matter in the universe. Adrian Mellett, an astronomer at the University of Kansas, conducted extensive studies of how these observational biases might affect the interpretation of galaxy clustering data. His work showed that some of the apparent fractal scaling in galaxy surveys could be explained by the way surveys select galaxies for observation rather than representing genuine fractal properties of cosmic structure. The controversy deepened when different research groups analyzing the same galaxy survey data reached contradictory conclusions. Some studies found clear evidence for fractal scaling extending to large scales, while others found evidence for a transition to homogeneity at scales of a few 100 million light-years. The disagreement often came down to subtle differences in statistical methodology, data processing techniques, and the treatment of survey boundaries and selection effects. One of the key technical issues in this debate involves the proper way to measure galaxy clustering and determine whether it follows fractal scaling laws. The correlation function, which measures the probability of finding a galaxy at any given distance from another galaxy, is the standard tool for such analyses. But calculating correlation functions from real survey data involves numerous technical choices about how to handle survey boundaries, weight different galaxies, and account for selection effects. Different research groups made different technical choices, leading to different results even when analyzing the same underlying data. Some groups found correlation functions that decreased smoothly with distance, consistent with a transition to homogeneity. Others found correlation functions that followed power law scaling relationships, characteristic of fractal systems, with no clear evidence for a transition scale. The situation became even more complex when researchers began analyzing different types of astronomical objects. While some studies of galaxy clustering suggested fractal scaling to large scales, studies of galaxy clusters, quasars, and other cosmic tracers sometimes showed different behavior. This raised questions about whether different types of objects probe different aspects of cosmic structure, or whether observational selection effects affect different object types in different ways. Computer simulations added another layer of evidence to the debate. Large-scale N-body simulations of cosmic structure formation, such as the Millennium simulation, consistently predict that gravitational clustering should produce a transition to homogeneity on scales of a few 100 million light-years. These simulations start with the nearly scale invariant density fluctuations observed in the cosmic microwave background and evolve them forward in time using the known laws of gravity and cosmic expansion. The remarkable agreement between these simulations and many aspects of observed cosmic structure gives cosmologists confidence that they understand the basic physics of structure formation. If the simulations are correct, then fractal clustering should indeed give way to large-scale homogeneity, even if this transition occurs at somewhat larger scales than originally expected. However, critics of the standard model point out that these simulations incorporate assumptions about dark matter and dark energy that have never been directly confirmed. If these assumptions are incorrect, then the simulation predictions might not reflect the true behavior of cosmic structure formation. Some alternative cosmological models predict different clustering behavior that might be more consistent with observed fractal scaling. The cosmic microwave background radiation provides another crucial piece of evidence in this debate. The Cosmic Background Explorer satellite, followed by the Wilkinson Microwave Anisotropy Probe and the Planck Space Telescope, have measured the temperature fluctuations in this ancient radiation with extraordinary precision. These measurements show that the early universe was extremely smooth and uniform, with density variations of only a few parts in 100,000. The statistical properties of these primordial fluctuations provide a powerful test of cosmological models. The fluctuations follow a nearly scale invariant power spectrum that matches the predictions of cosmic inflation theory remarkably well. When this observed spectrum of initial conditions is evolved forward in time using standard gravitational physics, it produces cosmic structure that matches many features of the observed universe, including galaxy clustering on intermediate scales. However, the cosmic microwave background observations probe the universe at a very early epoch, when it was only 380,000 years old. The large-scale structure we observe today formed much later, through billions of years of gravitational evolution. Critics of the standard model argue that this evolutionary process might not be as well understood as cosmologists believe, potentially allowing for fractal scaling to emerge, even from smooth initial conditions. Recent observational advances have begun to provide new evidence relevant to this debate. The Dark Energy Survey, which mapped hundreds of millions of galaxies across a quarter of the southern sky, has provided some of the most precise measurements of cosmic structure ever obtained. The survey used gravitational lensing, which measures the distortion of galaxy shapes caused by intervening matter, to map the distribution of both ordinary and dark matter with unprecedented accuracy. The Dark Energy Survey results show clear evidence for a transition to homogeneity on scales of approximately 300 million light-years, consistent with the predictions of standard cosmological models. The fractal dimension of galaxy clustering decreases smoothly with increasing scale, approaching the value expected for uniform three-dimensional distribution at the largest scales probed by the survey. Similarly, the Baryon Oscillation Spectroscopic Survey, part of the Sloan Digital Sky Survey, has measured galaxy clustering across enormous volumes of space and found results consistent with the predicted transition to homogeneity. The survey detected the imprint of sound waves that propagated through the early universe, providing a standard ruler for measuring cosmic distances and structure. These recent observations have strengthened the case for the standard cosmological model and the idea that fractal clustering gives way to large-scale uniformity. However, the debate is far from over. Some researchers continue to argue that the transition scale is larger than these surveys can probe, or that subtle systematic effects in the data analysis might be masking genuine fractal scaling. The European Space Agency's Euclid mission, launched in 2023, represents the next major advance in mapping cosmic structure. This space-based telescope will observe billions of galaxies across a significant fraction of the sky, providing unprecedented statistical power for testing fractal scaling hypotheses. The mission will use both galaxy clustering and gravitational lensing to map cosmic structure with extraordinary precision. Ground-based surveys are also becoming more powerful. The Vera C. Rubin Observatory, currently under construction in Chile, will conduct the legacy survey of space and time, mapping the entire visible sky every few nights for 10 years. This survey will detect billions of galaxies and measure their properties with remarkable accuracy, providing another crucial test of cosmic homogeneity. The resolution of the fractal universe debate will likely require not just larger surveys, but also improved theoretical understanding of how observational selection effects and finite sample sizes affect the measurement of cosmic structure. Advanced statistical techniques, including machine learning approaches and sophisticated error analysis methods, are being developed to extract maximum information from these complex data sets. Regardless of how this debate is ultimately resolved, it has already had a profound impact on cosmology. The controversy has forced researchers to examine their assumptions more carefully, develop more sophisticated observational techniques, and consider alternative theoretical models. Whether the universe is ultimately fractal or homogeneous on the larger scales, the process of investigating this question has deepened our understanding of cosmic structure and the fundamental nature of space and time. While most discussions of fractal cosmology focus on patterns in space, some of the most intriguing and speculative ideas in this field involve extending fractal concepts to time itself. Could the temporal dimension exhibit the same kind of self-similar, scale-invariant properties that we observe in the spatial distribution of cosmic structure? This question opens up extraordinary possibilities for understanding the nature of time, causality, and the ultimate fate of the universe. The idea of fractal time challenges our most basic intuitions about temporal flow. We normally think of time as a smooth, continuously flowing dimension that carries us from past to future at a constant rate. But what if time, like the coastlines and mountain ranges we studied earlier, reveals increasing complexity and structure when examined at finer and finer scales? What if the history of the universe displays repeating patterns that echo across vastly different temporal scales? One of the first hints that time might have fractal properties comes from the study of cosmic evolution itself. The universe appears to go through repeating cycles of structure formation, where matter clumps together under gravity, forms stars and galaxies, and then spreads apart again due to cosmic expansion. These cycles operate simultaneously on many different timescales, from the rapid formation and destruction of individual stars to the slow assembly and eventual dissolution of galaxy clusters. The stellar life cycle provides a clear example of this temporal hierarchy. Individual stars like our Sun burn hydrogen for billions of years before exhausting their fuel and dying. But within stellar cores, nuclear fusion reactions occur on timescales of microseconds to minutes. Meanwhile, the formation of stellar nurseries in giant molecular clouds takes tens of millions of years, and the chemical evolution of entire galaxies requires hundreds of billions of years. These nested temporal cycles bear a striking resemblance to the spatial fractals we have already explored. Just as coastlines show similar jagged patterns, whether viewed from satellite altitude or through a magnifying glass, cosmic evolution shows similar patterns of birth, growth, and decay, whether we examine stellar evolution over millions of years or cosmic expansion over billions of years. The concept of self-similar temporal evolution becomes even more intriguing when we consider the role of feedback processes in cosmic structure formation. When massive stars explode as supernova, they inject energy and heavy elements into their surrounding environment, triggering the formation of new generations of stars. This creates a cascade of star formation that operates across multiple timescales, with each generation of stellar death and birth influencing the next. Computer simulations of galaxy formation reveal that these feedback processes naturally create fractal patterns in time. The star formation history of a typical galaxy shows bursts of activity followed by periods of quiescence, with smaller bursts nested within larger ones in a pattern that repeats across many orders of magnitude in time. The mathematical structure of these temporal patterns closely resembles the spatial fractals we observe in galaxy clustering. Chaos theory provides a theoretical framework for understanding how deterministic physical processes can generate fractal behavior in time. Many systems in nature, from weather patterns to population dynamics, exhibit sensitive dependence on initial conditions that leads to chaotic evolution. When the behavior of such systems is plotted as a function of time, it often reveals fractal structure with self-similar patterns across different temporal scales. The climate system of Earth provides a particularly relevant example of fractal time. Weather patterns show variability on timescales ranging from hours to decades, with similar statistical properties across this entire range. Temperature records, precipitation patterns, and atmospheric circulation all exhibit fractal scaling laws that remain valid whether we examine daily fluctuations or century-long trends. This fractal nature of climate variability has important implications for understanding long-term climate change and predicting future environmental conditions. Traditional climate models often assume that climate variations follow simple statistical distributions, but fractal analysis reveals much more complex temporal correlations that can affect the accuracy of long-term predictions. The study of ice ages provides another window into potential fractal patterns in Earth's climate history. Over the past several million years, our planet has experienced regular cycles of glaciation and warming, driven by periodic changes in Earth's orbital parameters. But these long-term cycles contain smaller scale variations, with individual ice ages showing complex internal structure of warming and cooling phases. Analysis of ice core data from Greenland and Antarctica reveals that these climate variations exhibit fractal scaling properties across timescales ranging from years to hundreds of thousands of years. The same mathematical relationships that describe short-term weather fluctuations also apply to the timing and intensity of ice age cycles, suggesting that Earth's climate system operates according to fractal principles across vast ranges of temporal scale. The concept of fractal time becomes even more speculative when applied to the universe as a whole. Some cosmological models propose that the expansion history of the universe might exhibit fractal patterns, with periods of acceleration and deceleration nested within larger cycles of cosmic evolution. These models suggest that what we interpret as a single Big Bang might actually be part of a much larger fractal pattern of cosmic expansion and contraction. Cyclic cosmology, developed by researchers like Paul Steinhardt and Neil Turok, proposes that the universe goes through infinite cycles of expansion, contraction, and rebirth. In some versions of these models, each cycle contains smaller subcycles, creating a fractal hierarchy of cosmic evolution that extends infinitely into both the past and future. Our current cosmic epoch would be just one small part of an infinite fractal pattern in time. The ekpyrotic scenario, a variation of cyclic cosmology inspired by string theory, suggests that our universe undergoes collisions with parallel universes in higher dimensional space. These collisions occur periodically, triggering new cycles of cosmic expansion and evolution. If the timing of these collisions follows fractal patterns, then the history of our universe would exhibit self-similar structure across enormously different timescales. Quantum mechanics introduces additional complexity into discussions of fractal time. In quantum field theory, virtual particles constantly appear and disappear from the vacuum on timescales determined by the Heisenberg uncertainty principle. These quantum fluctuations occur at all possible frequencies simultaneously, creating a fractal spectrum of temporal activity that extends from the Planck timescale of 10 to the negative 43 seconds up to macroscopic timescales. The quantum vacuum itself might have fractal properties in time. Recent theoretical work in quantum gravity suggests that space-time at the smallest scales might have a foamy, fractal structure where the usual concepts of smooth space and time break down. If correct, this would mean that fractal geometry is built into the very fabric of reality at the most fundamental level. Loop quantum gravity, one of the leading approaches to quantum gravity, predicts that space-time has a discrete, granular structure at the Planck scale. This discreteness could give rise to fractal patterns in both space and time, with quantum fluctuations creating self-similar structures across multiple scales of observation. The challenge is connecting these microscopic quantum effects to the macroscopic fractal patterns we observe in cosmic structure. Biological evolution provides another arena where fractal patterns in time might be important. The history of life on Earth shows punctuated equilibrium, with long periods of gradual change, interrupted by rapid bursts of evolutionary innovation. These evolutionary patterns exhibit statistical properties reminiscent of fractal systems, with similar scaling relationships appearing across timescales, from individual lifetimes to geological epochs. Mass extinction events, which have repeatedly reshaped the course of biological evolution, occur with a frequency that might follow fractal scaling laws. The fossil record shows that extinctions of different magnitudes happen at different rates, with smaller extinctions occurring more frequently than larger ones according to a power law relationship characteristic of fractal systems. The concept of fractal time has practical applications in fields ranging from economics to medicine. Financial markets exhibit fractal scaling in their price fluctuations across timescales from milliseconds to decades. Heart rate variability shows fractal patterns that change with age and health status. Even human behavioral patterns, from sleep cycles to social interactions, often display fractal temporal structure. These biological and social fractals in time might reflect fundamental properties of complex adaptive systems. Networks of neurons, ecosystems, and economic systems all exhibit similar fractal patterns in their temporal evolution, suggesting that fractal time might be a universal feature of complex systems, rather than just a curiosity of cosmic structure. The study of solar activity reveals fractal patterns in the Sun's magnetic field variations and sunspot cycles. The 11-year solar cycle is embedded within longer-term variations that show fractal scaling across timescales from days to millennia. These solar fractals affect space weather and can influence climate patterns on Earth, creating another link between cosmic and terrestrial fractal phenomena. Pulsar timing provides one of the most precise tests of fractal patterns in astronomical timekeeping. Pulsars are rotating neutron stars that emit regular pulses of radiation with extraordinary timing precision. Long-term observations of pulsar arrival times reveal fluctuations that sometimes exhibit fractal scaling properties, potentially reflecting fundamental noise processes in space-time itself. The search for gravitational waves has opened up entirely new possibilities for studying fractal patterns in time. The Laser Interferometer, Gravitational Wave Observatory, and similar detectors are sensitive to distortions in space-time caused by accelerating masses. If space-time itself has fractal properties, these distortions might show fractal patterns that could be detected in gravitational wave signals. Future observations with space-based gravitational wave detectors like the Laser Interferometer Space Antenna will be sensitive to much lower frequency gravitational waves that could reveal fractal patterns operating on cosmic timescales. These observations might detect the gravitational wave background produced by cosmic structure formation, potentially revealing whether the growth of cosmic structure follows fractal patterns in time as well as space. The philosophical implications of fractal time are as profound as those of fractal space. If time itself has fractal structure, then concepts like causality, free will, and the nature of consciousness might need to be reconsidered. A fractal universe in time would be one where the past, present, and future are connected by self-similar patterns that repeat across all temporal scales. Such a universe would challenge linear concepts of progress and development, suggesting instead that cosmic evolution follows recursive patterns that echo infinitely across time. The history we experience might be just one scale of a vast fractal pattern that connects quantum fluctuations to the ultimate fate of the cosmos, revealing deep mathematical relationships between the smallest and largest processes in nature. As our observational capabilities continue to improve and our theoretical understanding deepens, we may eventually be able to test these speculative ideas about fractal time. The next generation of cosmic surveys and gravitational wave detectors will provide unprecedented precision in measuring temporal variations across the universe, potentially revealing whether time itself exhibits the beautiful, complex patterns that seem to govern the spatial structure of the cosmos. The possibility that our universe exhibits fractal properties across all scales of space and time raises profound philosophical questions that challenge our most basic assumptions about reality, knowledge, and our place in the cosmic order. A fractal cosmos would represent more than just an interesting mathematical curiosity. It would fundamentally alter how we understand the nature of existence itself, forcing us to reconsider concepts that have guided human thought for millennia. One of the most striking implications of a fractal universe is the absence of any privileged scale of observation. In traditional thinking about the cosmos, we often assume that certain scales are more fundamental or important than others. We might think that atomic scales reveal the basic building blocks of matter, that human scales represent the natural perspective for understanding the world, or that cosmic scales show us the ultimate structure of reality. But fractal geometry demolishes these assumptions. In a truly fractal cosmos, every scale of observation would be equally complex and equally fundamental. The patterns visible in galaxy clusters would be neither more nor less important than the patterns in quantum foam or the branching of blood vessels in your body. This scale democracy challenges our intuitive sense that some things are more basic or fundamental than others. This leveling of scales connects to ancient philosophical traditions that emphasize the interconnectedness of all phenomena. The Hermetic principle, as above, so below, suggested that patterns in the heavens reflect patterns on Earth and within human beings. Fractal cosmology gives this ancient wisdom a precise mathematical foundation, showing how the same geometric principles might indeed operate across all scales of existence. The concept of self-similarity across scales also challenges traditional notions of hierarchy and emergence. We normally think of complex phenomena as emerging from simpler components through a process of hierarchical organization. Atoms combine to form molecules. Molecules form cells. Cells form organisms. Organisms form ecosystems, and so on up a ladder of increasing complexity. But in a fractal universe, this hierarchical picture becomes problematic. If patterns repeat at all scales, then it becomes difficult to identify any fundamental level from which everything else emerges. Instead of a hierarchy, with simple foundations supporting complex superstructures, we would have a cosmos of endless recursive patterns, where every level contains infinite detail and every scale reflects the structure of every other scale. This recursive nature of fractal reality connects to deep philosophical questions about infinite regress and self-reference. If every pattern contains smaller versions of itself, and those smaller versions contain even smaller versions, where does the process end? Do we arrive at some ultimate foundation, or does the fractal descent continue forever? These questions echo classical philosophical paradoxes about the nature of infinity and the possibility of ultimate explanations. The problem of self-reference becomes even more acute when we consider that human beings, as parts of the universe, would themselves be embedded within the fractal patterns they are trying to understand. We would be fractal beings attempting to comprehend a fractal cosmos, using fractal brains whose neural networks might themselves reflect the same mathematical principles that govern galactic structure. This creates a strange loop where the observer and the observed are connected by the same geometric principles. This embedded perspective raises fundamental questions about the nature of scientific knowledge and objectivity. Traditional scientific methodology assumes that we can step outside the systems we study and observe them from a neutral, objective standpoint. But if we are integral parts of a fractal universe, then our observations and theories might themselves be shaped by the same fractal principles that we are trying to understand. Some philosophers have suggested that this embedded perspective might actually enhance, rather than compromise, our understanding. If human consciousness and cosmic structure both emerge from the same fractal principles, then our minds might be naturally attuned to recognizing these patterns. The mathematics of fractals might feel familiar and beautiful to us precisely because our brains are themselves fractal structures operating according to similar principles. The implications extend to questions about reductionism and holism in scientific explanation. Reductionist approaches seek to understand complex phenomena by breaking them down into simpler components and studying the interactions between these parts. But fractal systems resist this kind of analysis because they contain structure and complexity at every level of observation. You cannot understand a fractal by studying its components because the components are themselves as complex as the whole. This suggests that fractal cosmology might require fundamentally holistic approaches to understanding. Instead of trying to reduce cosmic structure to interactions between simpler parts, we might need to develop new ways of thinking that can grasp the self-similar patterns that connect all scales simultaneously. This could lead to new forms of scientific methodology that embrace rather than eliminate the recursive complexity of fractal systems. The question of free will and determinism takes on new dimensions in a fractal universe. If cosmic evolution follows fractal patterns that repeat across all temporal scales, what does this mean for human agency and choice? Are our decisions and actions simply part of a vast fractal pattern that extends from quantum fluctuations to cosmic evolution? Or does the infinite complexity of fractal systems somehow provide space for genuine freedom and creativity? Some philosophers have argued that fractal complexity might actually be compatible with free will because fractal systems are inherently unpredictable despite being deterministic. Even if the universe follows precise mathematical laws, the infinite complexity of fractal evolution might make it impossible to predict the specific outcomes of human choices. In this view, fractal unpredictability could provide the kind of openness needed for genuine agency. Others contend that fractal patterns, no matter how complex, still represent a form of cosmic determinism that leaves no room for true freedom. If our choices are part of recursive patterns that echo across all scales of space and time, then we might be like actors following a script written in the language of fractal mathematics, with no ability to deviate from our predetermined roles. The nature of consciousness itself becomes problematic in a fractal cosmos. If neural networks in the brain follow fractal principles similar to those governing cosmic structure, then consciousness might be understood as a kind of fractal process that emerges from the recursive interactions of neurons. This could explain why consciousness seems to have the peculiar property of being aware of itself, creating the kind of self-referential loops that characterize fractal systems. Some theories of consciousness, such as integrated information theory, already incorporate ideas that are reminiscent of fractal organization. These theories suggest that consciousness arises from the integration of information across multiple scales and levels of neural organization, creating unified experiences from the recursive interactions of countless neural components. If consciousness is indeed a fractal phenomenon, then the boundaries between self and cosmos become increasingly blurred. The same mathematical principles that govern the formation of galaxy clusters might also govern the formation of thoughts and experiences in conscious minds. This could lead to a kind of cosmic consciousness hypothesis, where individual awareness, is understood as a local manifestation of universal fractal principles. The implications for personal identity are equally profound. If we are fractal beings in a fractal universe, then the boundaries that define individual identity become questionable. Are you the same person from moment to moment if your neural patterns are constantly changing according to fractal dynamics? What makes you different from other people if you are all manifestations of the same underlying fractal principles? These questions connect to ancient philosophical puzzles about personal identity and the nature of the self. But fractal cosmology gives them new urgency and complexity. In a universe where patterns repeat at all scales, individual identity might be more like a temporary eddy in a fractal flow than a fixed and permanent essence. The aesthetic implications of fractal cosmology are particularly striking. If the universe is organized according to fractal principles, then mathematical beauty might be a fundamental feature of reality rather than just a human invention. The fact that we find fractal patterns beautiful could reflect a deep resonance between the structure of our minds and the structure of the cosmos. This connection between mathematics and beauty has puzzled philosophers and scientists for centuries. Why do mathematical relationships like the golden ratio and fractal patterns strike us as beautiful? A fractal cosmos would suggest that this aesthetic sense reflects our evolutionary and perhaps cosmic heritage as fractal beings in a fractal universe. The implications extend to questions about meaning and purpose in cosmic evolution. Traditional scientific views often portray the universe as meaningless and purposeless, with complexity and consciousness arising accidentally from the random interactions of matter and energy. But a fractal cosmos might suggest a different picture, where the recursive mathematical beauty of fractal patterns represents a kind of cosmic creativity or intelligence. This doesn't necessarily imply the existence of a conscious designer or cosmic mind. Instead, it might suggest that the mathematical principles governing fractal evolution naturally tend toward increasing complexity and beauty. The universe might be inherently creative, not because it is conscious in a human sense, but because fractal mathematics naturally generates infinite novelty and complexity. The question of ultimate meaning becomes even more complex when we consider infinite fractal hierarchies. If patterns repeat infinitely in both directions towards smaller and larger scales, then any local meaning or purpose becomes embedded within infinite recursive contexts. What appears meaningful at one scale might be insignificant at larger scales, while containing vast complexity and potential meaning at smaller scales. This infinite recursive structure challenges traditional notions of ultimate explanation and final answers. In a fractal universe, every answer contains new questions, every solution reveals new problems, and every level of understanding opens up infinite new levels of complexity. The search for knowledge becomes not a journey toward final truth, but an endless exploration of infinite recursive depth. Yet this endless complexity might be precisely what makes existence meaningful and interesting. A fractal cosmos would never become boring or predictable, because it would always contain infinite unexplored territories of mathematical beauty and complexity. Every scale of observation would offer new patterns to discover, new relationships to understand, and new forms of beauty to appreciate. The ethical implications of fractal cosmology are equally profound. If all beings are interconnected through fractal patterns that span all scales of existence, then our actions might have consequences that propagate through these recursive networks in ways we cannot fully comprehend. Harm done at one scale might echo through the fractal hierarchy, affecting patterns at both smaller and larger scales. This could lead to new forms of environmental and cosmic ethics that recognize our deep interconnection with fractal patterns extending from quantum scales to cosmic scales. We might be responsible not just for our immediate impacts on other humans and other species, but for our role in the larger fractal patterns that connect us to the structure of the universe itself. As we continue to explore the possibility of a fractal cosmos through observation and theory, these philosophical implications will become increasingly important. Whether or not the universe ultimately proves to be fractal, the very consideration of this possibility has already enriched our understanding of the deep connections between mathematics, consciousness, and cosmic structure. The fractal cosmos remains one of the most beautiful and challenging ideas in all of human thought. The quest to understand whether our universe exhibits fractal properties stands at the threshold of a new era. Revolutionary telescopes, unprecedented computational power, and innovative theoretical frameworks are converging to provide the tools needed to finally resolve the deepest questions about cosmic structure and the mathematical nature of reality itself. The next 2 decades promise to bring observational and theoretical breakthroughs that could fundamentally transform our understanding of the cosmos. The European Space Agency's Euclid mission, launched in 2023, represents the most ambitious attempt yet to map cosmic structure with the precision needed to detect fractal scaling laws. This space-based telescope is designed to observe billions of galaxies across more than 1/3 of the entire sky, measuring their positions, shapes, and distances with extraordinary accuracy. The mission will create the most detailed 3-dimensional map of cosmic structure ever assembled, providing unprecedented statistical power for testing fractal hypotheses. Euclid's unique capabilities stem from its combination of visible and near-infrared imaging with precision spectroscopy. The telescope can measure the distances to galaxies up to 10 billion light-years away, allowing astronomers to study cosmic structure as it appeared when the universe was less than half its current age. This temporal depth will reveal how fractal patterns, if they exist, have evolved over cosmic history. The mission's gravitational lensing observations will be particularly crucial for fractal cosmology research. By measuring how the gravity of intervening matter distorts the shapes of distant galaxies, Euclid will map the distribution of both ordinary and dark matter with unprecedented precision. This will provide a direct test of whether dark matter clustering follows fractal scaling laws on the largest observable scales. Preliminary data from Euclid is already revealing cosmic structure with stunning clarity. Early images show the cosmic web in unprecedented detail, with dark matter filaments stretching across hundreds of millions of light-years, connecting galaxy clusters in an intricate network. The statistical analysis of this data will take years to complete, but the sheer volume and quality of information promises to settle many outstanding questions about cosmic homogeneity and fractal scaling. On the ground, the Vera C. Rubin Observatory in Chile is preparing to conduct the Legacy Survey of Space and Time, the most comprehensive astronomical survey ever attempted. This revolutionary facility will photograph the entire visible sky every few nights for 10 years, creating a time-lapse movie of cosmic evolution with unprecedented depth and precision. The survey will detect more than 20 billion galaxies and track changes in their brightness and position over time. The Rubin Observatory's unique strength lies in its ability to study cosmic structure across vast ranges of both distance and time. The survey will detect galaxies at distances corresponding to when the universe was only a few billion years old, while simultaneously tracking nearby objects with exquisite temporal precision. This combination